Everybody can hear me? Okay. Now, before I talk, I have two things needed to announce. First, let Kelly to talk about.
There's sign-up sheets in the back on the tables out there. If you could sign in, that would be great. Also, there's evaluations. If you didn't get one, please raise your hand. I can please come around. And that will help us kind of help you serve you guys better. And if you want the CME credit, you do need to fill this out. Also on the back, you'll notice there's a speaker disclosure. So that's about it. Does everybody have one?
Okay. Second thing I want to announce that was the last week, last month's the talk where some, miscommunication happened. A lot of people came here and the speaker gave the talk at a different time. So that really, should be, apologize. The communication was broken between our division and the school planning the part. They give us the long time and the long different location and send an email to the, you guys is the different. So sorry about that. Okay. Okay, today I'm going to talk about the simple linear regression. Okay, my name is Mei-Jie Zhang. I'm the faculty at the Biostatistics. So if you have a question, just stop me. Okay, that's to get used to. Okay, this is the speaker disclosure. Basically, I have nothing, no relationship needed to be disclosed. Okay, here's the outline of my talk. First, I'm going to talk about what is called a simple linear regression. Basically, we wanted to present the relationship, the relationship between two variables, and we represented by linear here means it can be represented by a single line. So we need to review the equation of a line, the properties, and then because this real line is unknown, so we need to collect the data to estimate those parameters. So this is called the fit line to the data. I'm going to talk about once we get this result, most often we get it from computer statistical package, and then we need to interpret these results. So we'll talk about the interpretation, and when the linear regression, we fit the linear regression, we can do some prediction, okay? And also, because this we collected the random samples, and this is a random variable, so we get one single estimate, but we need to talk about how accurate our estimate is, because this will involve the confidence interval. And also we want to test whether this relationship are really significant, or this is there's two variables, there's no relationship at all. So this is related to the hypothesis test. And we also want to discuss the measuring the strength of the association between two variables, and what's the assumption of the linear regression when we do it, and when also at the end of the talk we'll talk about some special case when the predicted variables are not continuous, it's a binary. Okay, so how to handle that? So what is the linear regression? So here is the math. This is a linear regression is a method to describing the association between the outcome variable, sometimes we call dependent variable, and one or more predicted variable. This variable can be continuous. For example, the height of age for the kids. Okay, then the height depends on the age. So age is continuous. For example, from 5 years to 10 years. But it could be binary. If we're interested in, say, compare, say, 10 years boy and a girl. Here, boy, sex is the binary variable. Okay, it could be category. For example, if we want to study the height between the different racial groups, so it could be whites, blacks, Asians, Hispanic, or the others. So then this. So we want to present this relationship in a single equation. That's the linear regression means. Okay, there's a relationship between two variables, but this relationship can be described in a single line. Okay, this called that one. So we need to estimate the magnitude, the strength, and the statistical significance of the relationships, and also these, based on the developed linear equation, we can predict the outcomes. Okay, so for example, we study from age 5 to 10, we collect the death data, then we can predict the value, say what's the 6 years, the kids on the average, what's the height will be. So this is called the prediction. So, okay, what is the difference between the simple linear regression? That's here the simple means we only consider one predicted variable at this case, but often we will have more than one predicted variable, but the result can be generalized very simple, so we have emphasis on the simple linear regression here. Okay, and also in this talk we're focused initially on continuous predictors. At the end of talk, we will consider the binary predictor. Okay, and because this relationship is linear, it can be described by a line. The line can be presented like this way. Y is the dependent variable. It's called outcome variable. X is predictor, independent variable. What we give the x value, we know what is average value, expected value, or called average value for this outcome y. Okay, this is the relationship we're going to study. Okay, here's an example. Let's look at it. Now, this is a survey of women, and this blood sample drawn from 20 women, and measured the hemoglobin value, and actually some other values. I'm not going to use it in the example, so just consider hemoglobin. And also ask these 20 women what's their age and whether they had experienced menopause. Okay? And this data is published in the book. So the researcher basically want to know is this: what is the relationship between hemoglobin and age? Is there any relationship? If so, does the hemoglobin increases when age increases, or it decreases when age increases? So, and also we want to know how strong is that relationship. In other words, this strong means can hemoglobin be very accurately predicted just from knowing their age? Okay? So if 100% is strong, that means if I know the age, I know exactly what's the expected value for the hemoglobin. Okay? Accurately. But often we don't. Okay? So, and this also researchers want to know, is this relationship statistically significant? So to address this question, so we needed to, and also, for example, based on after we fit a linear model, fit a linear regression model, then we can answer questions such as what would be the predicted hemoglobin level for a 45-year-old woman, for example, on the average, okay, not on the observed. Maybe your sample has one woman, aged exactly 45, has some hemoglobin value, but that's not, we would say, predicted value. Those are the observed value. So this is the data set, 20 subjects, this is the hemoglobin levels, and this is the age, and this is the menopause. Now from the data set, you look at the table, it's very difficult to make any sense out of that, right? So but that's why we always like to make some plots, because plots tells a lot of the story behind the data. For example, this is called a scatter plot. This x-axis is the age, and this is the hemoglobin level. For example, we have one subject, say, for example, 45 years old. Her hemoglobin level is 15.1. So you can see that one, 45, and this one, this subject, hemoglobin is 15.1. We just make plots. Each 20 subjects, women, we have 20 plot dots. From this one, we get some sense out of that. Say, it looks like there's some relationship, right? Pretty strong. It's like age increases, like hemoglobin level increases, right? So the plots is very helpful before we do any analysis. Also, these plots later we'll see. It's a very nice way you can check whether the model is a good linear model, is a good model. For example, the linear model, that means this relationship can be represented by a single line. From here, looks like okay. The trend is increasing and also concentrated around the one line. So this data set probably is pretty good to fit a simple linear line. So what is the line? Now let's look at the equation of a line. Equation of a line, it can be represented the y equals a plus bx. That's the simple mathematics. A represents the intercept. That's the value of y when x equals 0. And b is called the slope. That is the change in y when 1 unit increasing in x. That's called slope. How fast it changes. So if we look at this line, okay, this is a line. What is A, what is B? Now from our definition, say any line can be represented by A and B, this equation. So A is the intercept and the B is the slope. So this one, A is very clear, is when x equals 0, that amount is called A. So we can look at this. This is A. And what's the B? B is the slope. This means every 1 unit of x increase, what is amount change in y? In this time, y changes positive. So in other words, the slope is positive. If the line goes this direction, then this changes negatively. Because this will go this direction, then the slope is negative. So when x increases, y decreases. Okay? So there's two parameters determines a single line. So in other words, if we wanted to fit a simple linear regression, then we need to figure out these two numbers. Once we find out this number, we know where this line should be. Okay? So here's the ones. Okay, in most realistic situations, the data do not fit exactly on a line. Okay, that's impossible. So the outcome, because our outcome y are random variable. You collect these 20 worms. If you collect other 20 worms, the value will be different, will not be exactly. Okay, so does y increase on average as x gets large? So this the question say we want to fit this line, and this means the y. What's this mean? Means y means the average value, expected value, okay, to this predicted value in this line. So if we look at our line, say for example, if the data is here, then line is here, so this will be the expected value. Then observe the value around this line. Okay? So now here's the thing. If we fit a linear regression model, we assume that there is a true regression line sit somewhere. Okay, we believe. And this on average expectation xy equals alpha plus beta times x. Here, e to the y is the mean or expected value of y. And y is alpha and beta, those are the true parameter. But those are unknown. Okay? We need to estimate it. Okay, that's the, So how to estimate it? We first need to collect the data. Without the data, we cannot do the good estimate. So once we collect the data, then we can estimate this alpha and beta we call A and B. So we can come up with any number we want to, but that's not a good estimate. What is a good estimate is this one. We try to find the A and the B, estimate, okay? Then the make it to be the error mistake as small as possible. Okay, this line close to the data as much as possible. That's what our goal will be. And the A and the B can be estimated by most statistical packages, almost all the statistical packages. Any questions? No. Okay. So how to estimating a regression line? So estimated regression line is the one we hope that fits the data best. So I coded that because what's called best, okay? So here that's one measurement to measure this is a fits the data best. Is this one. Y is the subject to error. So each observed we have y. And this, once we come up with this A and B align, this xi value, we can get this one is on this line. This is called predicted value. And what's the error we can make it? The mistake. That's the ones is or error or residual that is observed minus expected. The distance between these two. Right? See, we want this line, if the perfect fit, then this will be 0, then every data is sit right on that line. Okay, but it's impossible in the real data, so we try to minimize these values, error to be as smaller as possible, but not only one. We need to compromise all the data, right? So you can make it to be 0, but then the other one will win. So, but the problem is if we want to make all this summation of all these errors to be minimum, that's the problem because some are positive, some are negative. You add it together, it could be washed out. So we have to minimize the square of those, make it to be all the positive. So there is no cancellation going on. Then therefore, we will have the best fitted line, which minimize the total errors, actually is the sum square of errors. Okay? Will not have any cancellations. Okay. So this is just the formula, and we can see that one. See, these are the data. We have 20 observations. This we call poorly fitted, because if we don't look at all this fit, I would think the line should be somewhere along that way, right? That would be probably most close to all the red dots, somewhere along that direction. So if we fit this one, then the distance is very big for all those points. Okay, so this is called poorly fitted data. So the best fit one is called the least square fit. So in other words, here, the distance summation of all the square of this distance you add together to be smallest one. This is the one, it is called the least square fit. It has smallest sum of square of errors. Okay? Now, fit this one, that's fine, but how to do it actually can solve this by equation and by the data, but the easy part is this one. We don't need to do this because all the statistical package can work, will provide those numbers. You just put it into the data and you call this function, linear regression. You will come up and say A and B, estimate, standard error, confidence interval, all these things, p-value. So we'll discuss all this, what's the interpretation of this value. So what the statistical package will work for this one? Almost all of them. SAS, SPS, Stata, Minitab, the free ones are, it will work that too. It will all have this one. So from this data set, we get this, say, A equals 8.24, B equals 0.134. So that the relationship is this one. Hemoglobin equals 8.24 plus 0.135, 0.134 times the age every year. So this, we fit this line. So from this line, we'll talk about later, we'll see that one say, you give me the age, I can give you the expected value. For example, 30 times this one plus that, I get a hemoglobin level. So we can get very easy. Now, this one is the intercept, okay? That means age equals 0, but meaningless. But we have to use it. Otherwise, force this line cross 0. That does not make sense. Okay, diagonal, this origin. And then this one is the relationship tell us how much when every year increasing the age, what's the hemoglobin changes. Okay? As we see, it's a positive, so it's a positive here. That is a change every year. Hemoglobin level will increasing 0.134. Now we'll talk about later, is this B represents the strength of the relationship between age and the hemoglobin. Most people will think that, yes, right, you have large number means more increasing. Actually, no. This just tells us how the magnitude, why we'll talk about later too. I just briefly tell you, because this value, it depends on the unit of age, x. If I say age by x by age by every 10 years, then this certainly will be 1.34. So this B depends on the unit level of x. So it only tells us what's the relationship, but will not tell us strength of the. We want to later on develop a measurement, measure the strength between two variables, which is unitless, does not depend on the unit. If it depends on the unit, that's not good, because I can certainly say, well, I don't want to use, this age, most people using years. But if you think the length, you could be using meters, could be centimeters, could be millimeters, or then the B will be changed. So that's not a reasonable way to measure it. But I want to say this. We'll talk about more talk more later, because intuitively people always think that B measures how strength these two relationships. Actually, it's not. Okay, so how to interpret this A and B when the computer print out the result? See here, A is expected or mean value of Y for a person with X value equals 0. In this case, does not have meaning, because this means, say, well, the hemoglobin level for a woman at age 0, not born yet. Okay, so that what's a hemoglobin level? But we have to put this one. It's okay. So it's not necessarily meaningful. In some situation, it's meaningful because X is starting from 0. Okay. So if you wanted to study, say, follow-up after discharge from hospital, then X0 is the time from discharge. It has the Y value, so that's fine. But in this case, there is no meaning. Okay. But we have to do it because it's mathematical necessary. Otherwise, the line will cross the 0. That does not make sense. Here, the range in this data set is between 20 and 67. although based on the line, we can do prediction even outside the range of X age. So for example, what is the hemoglobin level for a 75 years old woman? From the line, it will tell us, but that's not good. Usually, we should not to X beyond the data range. That does not make sense because data does not support us to this value. The prediction does not. Okay, we don't have. So then, what is the B? B means say every 1 year increasing in age were associated with an increase in the mean value of hemoglobin that will be increasing about 1.34 on average, not on each individual. Okay, so then fitting this linear line, that is because we have a strong assumption called linearity. That means the increasing does not depend on where the X value is. So the hemoglobin value change from 21 years old, from 20 to 21 years old, they're same as 55 to 56 years. Okay? So that's the strong assumption, okay, because we assume the linearity. So that means every increasing 1 year of age, we're increasing hemoglobin level of 0.134, no matter where this age value started. Okay? So based on this linear equation, we also can use the linear regression model to predict the outcome for individuals with specific value of X. For example, if 30 years, although may not be in the data set, and this hemoglobin for this case, it equals 12.26. Okay, even there is a person in the data set, for example, 45, it equals to, the data is 15.1, but you fit this one is not exactly, because with this expected value, the predicted value is on the line, not on the observation. Now, we need to talk about the confidence interval. Say, well, okay, we get a data set. We collect the data. We get this estimate A and B. Try to estimate the true unknown parameter alpha and beta. Okay. Now, we collect another data set. It will provide me another set of the estimate. Most likely will not be exactly equals A and exactly equals B, because those are the random sample. Okay? So then, and therefore, the estimate, those one called the point estimate, a single estimate. Okay? We try to estimate this value, try to estimate the true parameters. Now, the series says this one, if these estimates are good actually, with the one sample, we may not exactly equals the true unknown. But if we do it repeat again, and again, on the average, you average all these estimates, we're getting close to the true unknown. Okay, so to overcome that, the problem, you will the simple from one single random sample. Now, then we say this one. The true unknown parameter alpha and beta, those are unknown. But we try to construct a confidence interval. Say, for example, 95% confidence interval for beta, which means we come up to this interval. It means the true beta is unknown. But we know 95% confident the true one should be within this interval. You have 5% chance will be outside this interval. But it's unlikely. So we are pretty confident the true one will be sit in. So this is called the interval estimate. Give us a sense what this true parameter, the range will be sitting in. Instead of single ones, we don't know how far this will be distance. Okay. So here that's all the things is I'm talking about. We try to construct the confidence interval for the regression parameter. In particularly, we are interested in the beta because this gives us how much the increase is, the relationship. Okay. Then the alpha, which is the intercept, only used for the prediction value. If we want to construct the confidence interval for the predicted value, then we need it. And also this confidence interval can be used as a test too. And besides that, because say if we have confidence interval, 95% confidence interval for beta, 0 is outside, which means the true one is unlikely to be outside. The 0 is outside. That means we say this one will not be 0. Okay, so it's significant. It's another way to do the hypothesis test. But also we can do a hypothesis test the relationship, whether this associations between the two variables is real or not. So in other words, we can compute the p-value. Okay, usually when p-value is small, less than 5%, we say there is a significant relationship between these two variables. Okay, so here the computer package often will provide us the estimated beta. It also will provide the standard error. Okay, we denote it by the SE, standard error of B, because there's standard error of A in this case. There are two standard errors. Okay, so now how to construct the confidence interval? Here's the basic formula. It is B plus minus standard error times a critical value. And this critical value depends on the number of sample size. For the small sample size, we use t-distribution, but neither require strong assumption. For the large sample, usually greater than equal to 30, we use a normal series. Because the central limit series, then we're just using normal distribution, Z. Okay, so let's look at how to compute these things. And this is the formula. Instead of C, then this time for small sample, this is the T. Now when T distribution, it depends on the degree freedom. Here's the N is the number of total observation. P is the degree freedom. In this case, we have 2, because one is alpha, the other is beta, A and B. So we have 2 parameters to estimate. So this totally N equals 20. So the degree freedom will 20 minus 2 will be 18. And then we can look the table and find out what is the critical value for that. We can talk about. And actually, computer package will print out the confidence interval for us, almost all the packages. So for the large samples, that will be a little bit easier than just the symmetrical one, be plus minus Z times. Z is the critical value for standard normal distribution. It is well known for the 95% most of the time. It is Z equals 1.96. Sometimes people just using 2 times standard error. So it's okay too. It's approximate. Okay? So in our example, we have a small sample, N equals 20. So we estimate B equals 0.134, and the computer estimated the standard error equals 0.017. So the degree freedom equals 18, as I said, 20 observation minus 2 parameter A, B equals 18. So you look at the table, you find out 90% confidence level for this T is the 2.101. So then we can do simple calculation, b plus minus 2.101 times the standard error, which equals 0.1 almost to 0.17. So that means we how to put this confidence interval when computer prints out this result, SAS or SPS. That means, well, the true slope is unknown, but we are 90% confident it should be sit between 0.1 to 0.17, the slope. As smallest as 0.1, as fastest as 0.17. That's the line, the slope. Lined like one possible this one and one possible that one. The range of that one. We observe the one is in the middle of that. Okay? So that's the way. The slope. So now, and also we know this one, that this interval does not include the 0. What does it mean? Means 0 means there is no relationship between. Hemoglobin equals A plus 0 times age. No matter what age, Y hemoglobin level are same. So that means there is no relationship. Beta equals 0, that means there is no relationship. So we know at a 5% chance this 0 will be outside. It's unlikely. We draw the data, one sample, it happened. So we'll say this relationship between age and hemoglobin is significant because 0 is outside this confidence interval. Does it make sense? Okay. So also we can do a formal test. What is the test we say? In this one, we want to test whether this slope equals 0. That means the non-hypothesis is beta equals 0. So what is our test statistic? That is b minus the non-hypothesis value divided by standard error of b. So which will have either the t distribution for small sample, z distribution for sample n greater or equal than 30 for large sample, 2 cases. So let's come back to our data set. The observed slope equals 0.134, and we do simple calculation based on the t distribution. The p-value is 0.001, so which means it's quite significant. That means we reject the non-hypothesis. Okay? Because this one, what this means, the data sees this one, it's unlike the chance we make a mistake is less than 0.001. Okay? So this is the p-value tells us what's the we say we reject the non-hypothesis. We say the slope does not equal 0. We can make a mistake. The mistake is less than 1 out of 1,000 times. So we're pretty confident where this is our conclusion. Okay. Okay? We made a correct conclusion. Okay? So therefore, we conclude that there is a significant relationship between age and hemoglobin. And also, I said this one, that the confidence interval means this increasing on average is a possible slope. The smallest is 0.1. The largest is 0.17. Our observed estimate one is 0.134. Sit between these two. Okay?
So,
yeah.
The hypothesis testing was only to generate the p-value?
Yeah. The p-value is the okay. When we do the hypothesis, we always need to set up called non-hypothesis and alternative. In this situation, alternative is a beta does not equal 0. Okay? There is a relationship between two. So what is the p-value means is if this beta equals 0, there's no relationship. Okay? I conclude, say there is a relationship. Beta does not equal 0. what is the possibility, what a mistake I can make, chance, probability. So here the test saying, this one say, if the null hypothesis is true, age and hemoglobin, there is no relationship, 0 at all, no relationship. Then I conclude, say, they are not true. There is a relationship. I can make a mistake, okay? Because the true one, nobody knows it. But the mistake, the chance is only 1 out of 1,000. So small, that's unlikely it will happen. I draw a single sample. It happened. I draw 1,000 times, I will have make one mistake. But now I draw the 1. How unlucky will be that will happen. So that's the one theory behind to say, yeah, we admit that we could make a mistake, make a wrong conclusion, but the mistake is a very small probability. The chance is very small. That's all about it, because the true one, nobody knows it. We try to collect the data to do the estimate, to do the testing, to do make the final conclusion. Okay? Because it's true one is unknown, we can make mistake. We try to minimize our mistake. And we're confident. We also need to make sure what's our error range will be. We can tell you. Say, I could make mistake, but the error chance to make a mistake is very small. So this is all about. Is that clear? Okay. Okay, now let's look at how to measure the strength, the association between two variables. As I said, often people think about the B is measures the strength, because the large means B means the slope very fast. So age increasing, Y hemoglobin increasing very fast. But that depends on the unit of age, X. So that's not good. So we try to come up with something that's the independent of the units of the X value. Okay, so another way is this one. We can look at this one. Strength of association refers to how close the points following the regression lines. If everything is a perfect fit, there's no error, very strong relationship between. Because there is a lot of the errors. That means, maybe something is not fully explained by age. Hemoglobin maybe can be explained by some other variable. Okay, so that's the measurement. We try to say is this one. The measures how much does age explain the difference in hemoglobin. So how to do that? If you already learned some, take some statisticals, sometimes you look the output, you print out the R square. Okay, R square measures the percentage of variability in the outcome Y, which is accounted by the regression on X. So means the Y predicted value, how much can be explained by the X. Okay, so R square, the range from 0 to 1. 0 means no relationship. R square equals 1. That means Y can be 100% explained by the X. In what situation? If with the real line, if a line, all the X and Y is perfect on this line. So that means Y is 100% explained by the Y. In this case, R square equals 1. If the distance is very large, that means it's not perfectly explained by X. So therefore, its worst situation is 0. We can come up with some example in later. So in our example, the computer prints out to say R square equals 77.4%. So the age explained the 77% of the variability in hemoglobin values. Okay, so therefore still there is 22.6% unexplained by age. Okay, because it's not a perfect fit. So what is how to calculate this R square? See here, if there is nothing, hemoglobin does not depend on the age. So age does not have any prediction. So what is the largest situation you can think about? This is the average line of the hemoglobin. Average. So there is the distance you add together is the largest one. Okay? So in this case, is we take the sum square of that one, sum square for each of this line along the residual mean is the 109. Okay, in this case, 109.62. And this the fitted line. So this the residuals is explained by this line. So we use this ratio divide by the total, this quantity. That means those are not explained because those ones outside the line. So therefore, we use that one 24.81 divided by that one equal 22.6%. These are not explained by the age. And 1 minus this 0.226 is the R square. That means represents this quantity is explained by the age. So that's the calculation. So when this R square equals 1, that relationship is very strong. Okay? Strongest you can get. Okay? So, but there is another one to represent. The R square from 0 to 1 does not have any direction. So then the Pearson come up a measurement is called Pearson's correlation. This is small r and little r. This is the square root of R square and also represents the direction. When B is positive, then the correlation R is positive, and when B is negative, then this R is less than 0. R equals 0, same as R squared, because there is no relationship. Okay? So in our weeks that are not explained at all, so in this case, in our example, slope is positive, so R equals 0.77. Square root of 0.774 equals 0.88. Okay? Range from -1 to 1, which give us represents the strength and the direction. Okay? So this is the either Pearson's correlation or R square both measure the strength of the relationship. Okay? Linear association. And now here's the one example, the situation we can come up. Say, for example, if this X and this the Y, of course there's strong relationship. Right? But this relationship is not linear, the increasing and the decreasing. If we force this data, say, ignoring this linearity assumption does not hold, I just fit a line, it should be here. Flat line. Right? Some the positive, some the negative should be here. There will be distance where residual will be smallest one. Then the B will be 0. Okay? And then also we can compute that one, R equals 0 and R square equals 0, which means, say, there is no relationship at all. But that's not true, because this the case is all the R and R square based on assumption that the X and the Y had a linear relationship. This case, there is a strong relationship, but they're not the relationship is not linear. So in that case, we're just using those one to fit. Does not make sense at all. Okay? So, and also we need to look at this one is called outliers. That's the ones is all the correlation we talk about the two is the R square and the correlation. They're all sensitive to the outliers. Why? Because it's we can look at this picture, and this curve here. Okay, if we're increasing, add one more data here, extreme case. So in this case, the direction changed because just by single one observation. So in this case, when this happened, when we first thing we needed to look at is data any mistake, error. Often it's like decimal points for the wrong decimal points, and sometimes you need to investigate whether this is the true value or this is typos or the lack of mistake, stuff like that. But sometimes it do happen. After you investigate everything, that's the data. So sometimes you need to exclude that data to make this study will be more sense. Okay, but for the one correlation we can look at is this another one called the Spearman's correlation, which does not depend on those, depends on the rank of these two. Okay, it's less sensitive to the outliers numbers. So why this one? It's the same thing like when we do study, not here situation. I'll give you one example. When we often report the values, we want to report a median, not a mean value. Why? Median, it is less sensitive to the outliers. Because for those large number, it's only the position, not how big that is. You report the mean, it makes that a value. Okay, so if you say you say your household income or whatever the values, okay, you're using mean or median. Say if the county Bill Gates lived in, well, if you report the mean, it will be very, very large. But that does not make sense. So you should report the median. That's the same thing here. We use the rank, does not use the value, which is less sensitive to those outliers, how big that value. We don't care, only care how this position, large position. Okay, so that's another way. This another way to report the correlation is called the computer program will report this Spearman's correlation as well too. Okay, but it's a bit complicated. I'm not going to talk how to get this, but it also measures the strength. Okay. So, okay. So so what is the assumption? Well, assumption is to say the relationship has to be approximately linear. As we say, if not linear, we ignore it. It will give us misleading result, like quadratic form. Okay, so then this one, and also that means the predicted error is unrelated to the predicted value. So in other words, the residue it should be there is no pattern. For example, if we look at this line, so the large of x, the residue is there is no particular larger than this residue. It's all have same. Okay, so that's the one. Oh, sorry. Okay. Oh, sorry. Yeah, and then the residue, the error need to be normally distributed. The residues should be all these residues are independent. So here's how to check those linearity. Scatter plot will tell us this relationship pretty good. It's approximately linear. And then independent, constant variance, it can do the residual plot against the fitted value. It should be no special pattern. Not a large of this predicted value has a large value. Okay? And then what's the normality assumption? We can call the normal plots and it should around this line. In this case, pretty okay. Computer can do that. And then in situation in check independence is pretty difficult. But when we have in 20 observations, each one has one observation value. So these are independent. we can assume. The only sometimes the problem is one individual has multiple observations. Like you do follow-up every week, next week. So because that individual has a high value, next time most likely will be high value. So that case. But it's not this case, okay? So now, this sense, it's a normality and the other constant variance are not too sensitive. The linear assumption is more sensitive because all our estimate based on the linear relationship. If does not have linear relationship, then of course will be wrong. Okay, so now this is the probably last part of the talk. Its time is almost end of the talk. What's happened when we have only binary variable? In this case, it is a two-sample t-test. Because x equals 2 values, we can code it as 0 and 1. Okay? So in this case, when group equals 0, we code group equals 1, we code x equals 0. This is A, average value. And this group 2 is A plus B. We test there is a treatment effect. Test B equals 0 on average. So when small sample, which is this becomes to a two-sample t-test. And when for the large sample, we can use a linear test or use the normal test. Okay, using normal approximation. Okay, so here is the final caveats. And so as I mentioned many times, the large B does not mean strong relationship. It just tells us whether this mean, how does it, so it only measures whether there is an association and the direction of the association and what's the increasing of Y for every increasing 1 unit of X. Okay? And the correlation, now this one, let me explain that. The correlation does not imply the causality. What that means is this one. Well, it's only measures there is a strong association. Does not necessarily we can say Y is caused by X. Because X could be silicon values of the others. Okay? So hemoglobin, we say there is a relationship between age. One thing is not 100% explained. Maybe some other variable can be. Or it could be slow age by some other variable really influence the hemoglobin level. Okay? So this correlation only represents how strong these two variables are associated. Okay, here's I came up some simple books for. One is I give 3 books, and these are the relatively simple books. A good chapter talk about the simple linear regression. Okay, and I have to. This will be available on our department website slide, so don't worry about it. And I have to mention that one. This is available at the slides available on our website, and also I have to show these slides. That's the ones we have job in consultant for the CTSI. So these are the schedules at the Freda Children's Hospital, and this will be in VA, and these are the in Marquette universities. Time and the place. It's also available on our website. Any questions? No? Okay. So you haven't filled if anybody has not filled this evaluation form, please do. Okay?